Today's talk or today's video abstract will be divided into 3 parts. One, actually, I'm gonna say the background material first, 0 background, which will be pretty long for background. And then 1, construction of the Euler systems, construction of our Euler systems. Well, or rather, construction of the points that will become Euler systems. And 2 will show these points are actually indeed Euler systems. 3, application. And the application will be an analog of Victor Kolyvagin's important seminal work on the ranks of rational points of elliptic curves. Well, in our case, modular abelian varieties of level gamma 1 of n. Yeah, sorry, just go back to the previous slide. Well, of these 3 parts, of course, we work hard on each part. And even though on the 3rd part, yeah, we work hard on it. We work hard for it. And we in fact made some technical improvements as well. And also we worked hard on clarity. The real originality of our work lies in the 1st part and perhaps the 2nd part secondarily. Again, the real originality of our work is really the 1st part and well, to some extent, 2nd part. All right, so the background first. Our work is really to imitate or generalize Birch's construction of Heegner points to a wider family of modular abelian varieties. So well, this goes back to Kronecker. So Kronecker already knew, I think it was Kronecker, already knew that J, this is a J invariant or elliptic modular function, if you will. J, say n is any integer, say I guess well, safely bigger than 1. The pair of numbers j of tau and j of n times tau is in fact a solution, always a solution of a rational polynomial, which sometimes called modular equation. Yeah, following Kronecker or somebody, let's call it P sub n of xy. So this is called a modular equation or something. It's a rational polynomial or, if you will, an integer polynomial. Okay. So in a way, this is a model, an affine model for an affine model for the modular curve. y0 or y0 of n. And in fact, because this is a rational polynomial, it's an affine model over Q. Okay, so this is an explicit way to define an affine model for a modular curve y0 of n. And this, this has been known for a long time, probably going back to Kronecker. All right, what Birch noted is from the classical results of a class field theory. Okay, let's say K is an imaginary quadratic field, quadratic extension. Then what Birch noted, Brian Birch noted was that for each positive integer n, we can, well, not just any choice, but we can carefully choose what can be called quadratic third, some quadratic, well, some numbers tau sub n, and k, in this imaginary quadratic field k, and I forget, but I think it should have a positive imaginary part. So this is the upper half plane. So that, okay, so let's say C sub tau n is this point given by this moduli expression. Oh, sorry. And he noted that well, again, by a careful choice of tau sub n, this is defined over a pretty narrow choice of class field. This is called a ring class field. This is a ring class field. The ring class field of O sub n. I'm going to explain what it is shortly. Yeah, it's called ring class field in the sense that so O sub n, as you may know, if you're familiar with this stuff, is the order, what's called the order, a subring of O sub k with conductor n, and L sub O sub n is called ring class field in the sense that its Galois group over k is canonically isomorphic to the class group of O sub n. Yeah, I forgot to write it. I forgot to write it down on my note, but I think that's what it is. Okay, so just a second. So so this point, what he calls Heegner point, is defined over this field, and he called it, he named it after Heegner in the sense that was for some philosophical reason that it's defined over unexpectedly a small class field extension or something like that. Anyway, and moreover, moreover, these points satisfy a very strong relations, a large set of relations, distribution relations and congruence relations. So first of all, okay, so these are the points on the modular curve, but we can always find what's called the modular parameterization, right? All right, so y0 of n is of course a sub, well, is embedded in x naught of 0, x naught of n, and there's always the compact by adding the cusps, and you can always find well, all right, well, let me actually do it properly. So say y is a new form, say new form of level gamma 0 of n of weight 2, and say then yeah, you can always find by using one of the rational cusps, you can always find the map from the modular curve to this Jacobian, and then by taking a quotient given by the Hecking algebra and this new form f, you can find a quotient. Actually, for convenience, for simplicity, let's call it E, in the sense that we have an elliptic curve in, well, we're thinking about elliptic curve in particular. Yeah, sorry, I think I was rambling on a little bit, but anyway, so there's always this modular parameterization from the modular curve to an abelian variety associated to a new form of the given level. Okay. Then we'll let C sub tau n denote the image of C sub tau n. Okay, we'll just use the same notation for simplicity. So this is actually a point on an E. All right. Then he showed that these Heon points satisfy a bunch of really nice, strong norm relations. So the trace, or the, well, you can call it trace or norm of Heon point over the ring class of conductor n times L is AL of F times C sub tau n. If L, by the way, L is a prime number, and if L is prime to n times n, and L is inert, inert over K over Q. Well, you can call it that's the first distribution relation. And actually, what if L is not prime to n, but rather L is L divides n. Well, in that case, well, that's important too. In that case, the norm is AL of F times C tau n minus C tau n divided by L. If L divides n. And I should check the paper, but I think actually in this case L doesn't need to be inert, but I'm not sure. So I should check. And the third there's what's called the congruence relation. That's a little more complicated. Say L. Okay, well, say L is a prime to discriminant of K. That's not a big deal. Say V is a prime ideal of K1, the Hilbert class field, or rather in our notation, L sub O1, I guess, prime of K1, any prime above L, and say W is any prime of L sub OL above V. Then the reduction, well, yeah, you can reduce the Higner point, right? You can reduce the Higner point mod V, mod W. Sorry. So this is a Higner point of conductor L. And you can reduce it, right? We can reduce it mod W. That is equal to well, this is Frobenius, L Frobenius of reduction by modulo V of C, making a point of conductor 1. Yeah. Yeah, I don't know who proved it, but I think it first appeared, the first paper I saw, this is Kolyvagin's paper. So what Kolyvagin call the point, or cohomology classes or something that satisfy these 3 properties, he called them Euler systems. So this family of points is an Euler systems and Kolyvagin's language. And well, it's now a common, well, and we all use this name. And using these properties, and this is a huge machinery. Well, Kolyvagin developed a huge machinery, very sophisticated, and it's pretty difficult to handle, but very, very, very powerful. Kolyvagin show that okay, well, this is a little okay, well, I'm simplifying his result a little bit. Yeah, so for example, this is just an example. For example, say chi is a character of Galois group of k of 1 over k, and say chi bar is chi conjugate is chi. For example, the trivial character, perhaps the most interesting case. F C1, the Higner point of conductor 1, well, the chi part of it is not torsion. Then E of K1, well, the chi part of it has rank 1. The actual result is a little stronger because he actually showed that the Selmer group has co-rank 1. So actually, his result implies something about the Shafarij-Tate group being finite. Okay. Okay. So inspired by Birch and Kolyvagin's work, well, we have to go back to Baziz's work. Two of us, Daeyeol Jeon and Chang Kim, have worked a lot on Baziz's work. What he did was he gave an explicit description of a modular space Y1 of n. And how he did it was he gave an description by certain modular functions, and I'm going to explain it. All right, so all right, so Y1 of n as opposed to Y0 of n, Y0 of n, is the modular space, well, roughly, modular space of the pairs of elliptic curves and their n torsions. Well, more precisely, a n torsion, a specific n torsion. As opposed to Y0 of n, Y0 of n is modular space of elliptic curves and their subgroups of subgroups of cyclic order n. Now there are many ways to write down an elliptic curve, right? For example, there's a Weierstrass equation, or there are so many of them. But one way to describe all elliptic curves is that, well, we know that every elliptic curve is expressed means I guess has a model, or has by change of variables or something. What's called Tate normal form. Tate normal form. Let's call it following Jeon and Kim's notation. Let's call it E of B C, B comma C. So that y given by y squared plus 1 minus c xy minus by is x3 minus bx2. And obviously it has one rational point, which is 0, 0. Okay, 0, 0. And so, in fact, we can identify y1 of n as pairs of elliptic curves given by this equation and this n torsion point. Well, if it is n torsion. Okay, so how do we do it? So how Baziz did it? Well, he first noted that, all right, so one way to identify a pair of an elliptic curve with n torsion is by Weierstrass equation and Weierstrass P functions. So on one hand, you're given what you have an elliptic curve given by a Weierstrass equation. And on the other hand, you can specify one explicit n-torsion point given by P of 1 over n, and this is lattice. This is lattice given by tau 1 and P prime of 1 over n lambda, the lattice lambda tau. So this is one way to describe every pair of elliptic curve and n-torsion, right? Another, well, then because every elliptic curve is can be converted to take normal form, and the given point can be converted to 0,0. You can convert this to take normal form of, well, BC, the parameters of BC, but now there are functions of tau, if you will, and 0,0. And if you work hard, you can in fact write down what these are precisely. That's what Bazis did. That's what Bazis did by what he called division polynomial or division algorithm or something. Writing down what they are precisely is not very helpful for now. It's enough to say that they are some rational functions of Weierstrass P 1 over n of this lattice, and the Weierstrass 2 over n, well, and the Weierstrass P prime 1 over n, Weierstrass P prime 2 over n. Yeah, so they're rational functions of the combinations of these four, and it's just, yeah, that's what they are. And they're the modular functions of level gamma 1 of n. Okay. So, well, it stands to reason that well, I mean, we all know that these points, for quadratic surds, when tau is a quadratic surd, these are not necessarily algebraic numbers. In fact, they're likely not algebraic, but when they're properly combined, these modular functions have algebraic values for quadratic surds, right? Okay, so again, say K is imaginary quadratic extensions. Okay, and say tau is again K intersect upper half plane H. So tau has positive imaginary part. Now suppose the order, the subring of O sub K of conductor C, well, here C is an integer prime to n, well, positive integer. Suppose it acts on the lattice lambda tau. In case you forget, lambda tau is a lattice generated by tau 1. Okay, then let's say piece of tau. Oh, by the way, yeah. So let's go back to this slide. So this indicates that, in fact, y1 of n is determined. Well, all the points of y1 of n is given by the pairs of b tau and c tau. Okay. Yeah, so let me just write it in this corner. So B of tau, C of tau, or bases show that actually they satisfy a certain, well, I don't remember this notation, maybe it's a phi sub n or something. They are the solutions of some integer polynomial phi sub n of xy, and therefore phi sub n of xy is like an affine model for y1 of n over q. Affine model over q, and phi of tau comma c of tau is considered to be a point on y1 of n. Well, when it's considered an affine curve over q. Okay, and so that's the key to our work. That's the key to our work. So let's say piece of tau is a point given by b tau c tau. So that's that's some point. We roughly know it's an algebraic. It has algebraic coordinates, but we don't know its definition field yet. So let's just say it's defined over algebraic closure for now. It turns out in fact, this point is defined over a ring class field L sub OC of n. So this is called an extended ring class field. Of level n. Yeah, I don't think it's helpful to define it in this introduction. Roughly, a ring class field has conductor and ray class field has level, and this is a ring class field but with level n. That's a rough way to describe it. Okay. And of course, I don't want to prove it now. We proved it by applying judiciously main theorem of complex multiplication and nothing more. And you can see why. Because you see B of tau, C of tau, these are rational functions of some combinations of Weierstrass-Tate functions, and therefore it makes sense to use the theory of complex multiplication, main theorem of complex multiplication. I guess you can possibly use Shimura reciprocity law. But I think that using main theorem of complex multiplication is much easier, much straightforward, and also probably more Yeah, it could. At least in this case, it's just much easier. Okay. Again, well, I don't know whether you can use the Shimura reciprocity law, even though actually we mentioned in the paper that you can probably use it, but we don't actually know. We used the main theorem of complex multiplication and nothing else. And actually for the rest of the paper, well, to show that actually over the systems, we use nothing other than main theorem of complex multiplication, possibly due to our lack of foresight, maybe. But anyway, okay. Now we're gonna show there actually they're actually Euler systems. Okay. So this is getting long. Let me rush a little bit. Okay, say F is a new form. Oh, by the way, so obviously, we must pay respect to Birch's work. Obviously, this is all inspired by Birch's construction of Heon points, because when we looked at Baziz's, after Jeon and Kim's, Chang, Kim, and Daeyeol, Jeon's years of work with Baziz's work. When we looked at Baziz's work, we realized that maybe we can use it to do something like what Birch did. And turned out, actually, yeah, it was very possible. So yeah, this is a good place to pay respect to Birch's amazing work. All right, now our next step was to show Euler systems. All right. Again, like in Birch's case or Colli-Vaughan's case, well, now F is a new form of level, obviously, gamma 1 of n, not gamma 0 of n, obviously. Okay, so that's the key difference. Whether the level is gamma 1, gamma 0 of n, that's Heon point. If the level is gamma 1 of n, that's our point, generalization of Heon point. Okay, then we can fix a modular parameterization from x1 of n, of course, y1 is like subcurve, if you will, of x1 of n. And by choosing a rational cusp, in this case, actually, we chose 0 because we knew it's rational on x1 of n by the result of Og. By Og, we knew that the cusp given by 0 is rational. That's slightly different from x0 of n. But anyway, by using the rational cusp, we can you can always find the map from x1 of n to its Jacobian, given by, say, p to the divisor p minus 0 or something. Yeah, for a given new form, you can find the quotient of this Jacobian, right? And well, you can find the quotient of this Jacobian is an abelian variety associated to F. And if you will, you can call it the modular abelian variety. Okay, so under this map, okay, well, so let's remember this map. Okay, and okay, let's say K is the usual description Q of root D, square root of D. So D is a negative square free integer, okay? And we'll fix tau, a number tau. The tau will be root t if t is not congruent to 1 mod 4, and root t plus 1 over 2 if t is congruent to 1 mod 4, but the usual stuff. All right. Then for any integers AC where c is positive and c is prime to n, well, capital N. Well, let's say tau prime is a plus tau over c. Well, then well, obviously yeah, then obviously by the previous slide, p sub tau prime is a point of, well, or rather why not? Why is it 1? Y1 of n over the extended range class field, right? Well, you know, well, for simplicity, we let the same notation denote mu sub f. Mu sub f is modular parameterization at you know, map from here to here. Let this denote mu sub f of this point. Okay, so this is actually point of this abelian variety over L sub O sub C of n. Oh, by the way, so because of the way we define, like this is rational and so on, this map is defined over Q, and that's the point. Then, yeah, so now we have a point on an abelian variety, just like taking a point. Then, just a second. Then we have a bunch of norm relations, kind of like taking a point, or well, yeah, exactly like taking a point, except some differences, obviously, because the level is gamma 1 of n. Therefore, for example, the new form has a character, non-trivial character, possibly. Okay, say p is a prime. And okay, say just a second. C, in case I forget, yeah, C is this number, okay? Yeah, this is how tau prime is defined. Tau prime is A plus tau over C. Okay. Oh, sorry. Where was it? Okay, say C is prime to Pn, and P is congruent to 1 mod n, and say P is unramified and inert over K over Q. Okay, just like, well, just like in the Heon point case, but this is new. Yeah. Then sorry, the trace of L O sub CP n over L sub O C n of P tau prime plus any integer j over P is a P of F times tau prime. So j is any integer. 2, sorry. Actually, this was 4.2. This is 4.4. Now, again, say P is a prime and so on. This time, say P divides C. P divides the conductor. And P is prime to N, and the discriminant of K over Q and so on. Then, well, but not necessarily. P is not necessarily inert, unlike this case. Then the trace of O sub CP comma N over L sub O sub C N of P tau prime plus J, again, any integer J over P is again A sub P of F times P tau prime minus epsilon of P. Oh, this epsilon is the character of new form F times P P times tau. Yeah, I'm not sure I copied it correctly. On my note, it says P times tau. I won't write it down, but this epsilon is the character of F, the new form F. Okay. And what? Further, this is given by modular mod torsions. Torsions of A sub F over the definition field. Definition field of the cusp. Of cusp infinity. So yeah, actually, this doesn't depend on anything else, right? So by multiplying some fixed number to everything, you can actually get rid of this condition. Okay. So anyway, so I'm saying that it doesn't seem to be a big deal. Now, so these two are sort of distribution relations or norm relations. Now there's a congruence relation. Yeah, there's a congruence relation, just like in Kolyvagin's work. Again, say P is a prime. In this case, again, so again, like this case, say P is inert over K over Q. Yeah, I won't write it down. And again, this condition P is congruent to 1, mod N, and so on. And P is prime to C, and so on. Okay, say lambda is prime of L sub O C N, the ring class of conductor N, conductor C, level N. So say lambda is prime above P, any prime above P. And yeah, say lambda prime in turn is a prime of now L sub what bigger ring class field, O sub CP of level N, well, above lambda. Then And then the congruence relation is p plus 1 times the reduction of lambda prime of p tau prime plus, again, plus any integer j, for example, 0, divided by p is equal to p plus 1 times the pth Frobenius image of the reduction. Well, of course, pth Frobenius is possible because these are all reduced by prime of residue characteristic p, reduction lambda of t tau prime. You may notice that this is slightly different from Colley-Vaughan's congruence relations, like the presence of p plus 1, but doesn't seem to be a big deal, honestly. I don't think it's a big deal. And how you prove it? Well, you have to use, obviously, Eichler-Shimura relations, and also you need to use the fact that is inert, basically inert over k over q, and also you need to use the fact that lambda is a prime of a Raycloss field above an inert prime, and therefore it actually splits completely, I think, and so on. But anyway, yeah. So these are the things that you need to use to prove this congruence relations. I need to say one more thing about this. So, when we say Euler systems, there's no one fixed set of rules. It depends on the case. Even though the anti-cyclotomic Euler systems by Colley-Vaughan was the original one, actually other Euler systems tend to have a little different rules. For example, if you can find this in Rubin's book on Euler systems, like in cyclotomic case, or I don't know, or probably other cases, the congruence relations are normally not one of the conditions for Euler systems. Well, perhaps because well, if you define Euler systems a little differently, then you might need to have stronger conditions on some and weaker conditions on others, and so on. You can find this in Rubin's book. But anyway, so other Euler systems have normally different rules. Although these two distribution relations, these tend to be constant in all definitions, like cyclotomic units, elliptic units. Well, when you manufacture Euler systems, you need to do some manipulation on them, and so on. Yeah, they all satisfy these distribution relations in one form or another, or Kato's Euler systems given by a more abstract version of elliptic units. Elliptic units on universal elliptic curves, and when the Kato constructs this, what he calls Chern class maps, and he uses some smart twist of cohomology groups in a very smart way, and spectral sequence and so on. But anyway, but this is not like that. This is an anti-cyclotomic Euler systems, and therefore you need congruence relations, and they are important, often important. Yeah. Okay, so So that's, and therefore, yeah, these points that we constructed, piece, well, let's call them P sub tau prime, I guess. Tau prime varies, I guess. Well, okay, so there's a set of over the tau primes. This isn't a set of Euler systems. So that's what we did. So that's the bulk of our work, construction, and show that they are in fact Euler systems. And then using them, we show some rank results. So this is an analog of Colley-Vaughan's work. Again, we had to work hard for this lost result. And in fact, I think we made some technical improvements as well. So hopefully it looks better. But the real originality of our work is in the first part and second part. So theorem 5.48 in our paper is that, okay, say C is bigger than 0 and C is prime to n. Let's say for simplicity, let's say H is the ring class field, extended ring class field, L sub OC of level n. And let's say, suppose its degree over K is prime to P. The case where this is not prime to P is also important, I can imagine. Possibly it's better to use Iwasawa theory for it. I'm not sure. I haven't thought about it. I haven't thought about it, but it doesn't mean that I will never think about it. Yeah, we might come back around to this and think about the case where this is not prime to P at some point. But anyway, okay, say the chi is a character of the Euler group of K over H over K. And just like in Colley-Vaughan, assume that chi bar is equal to chi, like again, like a trivial character. And actually, I think that these characters have a name, genus character or something, but I don't remember. In our paper, we suppose that there's a canonical well-known map from the Galois group, absolute Galois group, G sub K, to the automorphisms of group of automorphisms of the residual representation, or just pi torsions. I don't have time to explain what pi is. It's roughly, let's say, p, p torsions. But A sub f might have usually have a bigger a bigger ring acts on A sub f, right? So let's say some pi. You can imagine it's just like p. But anyway, so suppose this is surjective, and we know that it's often surjective, right? Yeah, it's one of the assumptions that we often make when we apply Euler systems. Normally, with more work, we can get rid of this annoying condition, but let's assume it for now. It's very helpful. And importantly, suppose our point just again. I think. Oh yeah, I should explain. I should recall what pi is. You might remember pi is like either root d or 1 plus root d over 2, depending on whether d is congruent to 1 or not, mod 4. All right, so suppose P sub tau over C, well, the chi part of it is, let's say, not torsion. Okay. And we can imagine that this can be determined by some analog of Gross-Zagier formula, but yeah, it is something else that we can imagine we will be doing at some point. But we don't want to deal with it for now. Then we show that the Selmer group of I don't want to use the notation in our paper. So let's say, I think this is equivalent to the result in our paper. So say the chi part of the Selmer group. Sorry, that's probably not right. I guess probably it should be H has rank 1. Sorry, co-rank. It should be co-rank because it's Selmer group. For example, so therefore actually it implies that A sub F of H, what the chi part of it has rank 1. And also, it should imply something about Shafarevich-Tate group, like the P primary part of Shafarevich-Tate group is finite. Okay. Anyway, so that was our last result in the paper. So if you managed to listen to the whole thing, sorry that it's been very, very long, and thank you for listening. Bye.